Hi, this is Prudhvi and our topic is Constraint-Graph based compaction. And our batchmates are Sethupathi and Tushar. I'm going to tell the introduction part, and they are going to explain what are the algorithms there in this. And first of all, I want to tell you about what is compaction, and its compaction in reducing the space. It's actually it will be observed in layout. The operation of layout area minimization is called layout compaction. Actually, with these layout compaction, we can reduce 20 to 30% of the space which is left out in the chip after the routing. Actually, this compaction is based on space between the feature, size of the features, shape of the features. Actually, what is the feature is that actually in layout we will have polysilicon diffusion, these rectangles. Those we name it as features. And what the problem formulation is that we have a set of these m1 m2 mr. These are rectangular blocks that I have tell you, and the minimum feature size will be s of mi for all I, and the minimum separation between the mi and mj between the two rectangular blocks is d of mi and mj. What is our objective is to minimize the layout such that the size of our that block should be greater than what is there in the features minimum feature size, and the distance also what we have reduced, it should be minimum greater than what is the minimum separation between the mi and mj, or otherwise we will fail the rules, and it may cause the drc problems. So these are the objectives we have to follow. Now coming to the compact algorithms, these are based on minimum distance between features. I have told you features is nothing but rectangular blocks, polysilicon diffusion. These are constant graph based and virtual grid based. All these are 1D compaction, that is we can reduce only in one direction. We can These are based on one direction, and based on direction movement features also we have 1D compaction, 1.5 compaction, 2D compaction. Actually, it is easy in 1D compaction. In 2D compaction, it is very difficult to do in two directions. Actually, it is easy in 1D compaction only. We will reduce the space, and we can therefore improve the chip layout. And this constant graph based compaction, mainly it will derive like this: G is equal to V comma E, where V is the vertex represents a component, and E represents set of V, H's represents constant. Means actually V is the component what we have taken, and E represents the constants. Which are the constants we have to follow to reduce the space between the layouts. The E nothing but edge, that constraint I will show in the next slide. Actually, the constraint types are connectivity constraints and separation constraints. I will explain in the next slide. The connectivity constraint is that if two features x and y are required to be within a distance s of each other, actually it is dependent on connectivity. Let me take this. This is as one block, and this is a, I will show you here. This is a polysilicon, and this is some diffusion. If you want to connect these two, we should have some minimum width and minimum space we have to allocate to connect these two. That is the s. That is the s we are representing with the two blocks. That the minimum space required for that to allow attach these two. So this s represents the minimum. We should have some width space to attach these two. In the layout we have seen in the CAD also, while we are connecting we have some 2 lambda, 3 lambda between two metals, 2 lambda between oxide and gate. And here we show x and y. It is represented as minus s, because s represents the distance, but minus s represents the what is the minimum connectivity distance it should have to connect these two rectangular blocks I have told you. This is the constraint, connectivity constraints. This is a V vertex. I have shown in a previous slide. This G is equal to VE. V is the these vertex, and E is the these constraints, which is the node edge. Sorry, this is the edge, and these are V, these are E. This is the connectivity constraints. And now coming to the separation constraints, it tells about only the distance what we have to maintain between the two blocks. Here the two feature size xy are required to be at least d units apart from each other. These are the vertex, and this is the edge which is representing d. This is the d minimum distance should be between the two blocks. This is the separation constraints. Now going to any one of the technique. Actually these constraints, if we have no constraints, we can reduce the space. If there are constraints, we have to look at what are the constraints while we are while we are reducing the space. We can see what are the connectivity separation constraint, and based on that we can reduce the space. That is why we use these connectivity and separation constraint. If there are no constraint like this, there are no separation not needed between these distance, we can easily reduce the space. If we have this constraint that we should have the minimum s, minimum d, then we have to look at carefully and we have to do the reduction in the space. And now let me show you one of the technique, the shadow propagation method, which we can easily know. One of the best known and widely used technique, generating constraints. It is used to generate a constraint. We can easily know what are the constraints to reduce the space. Let me explain you in the slide. This is the blocks. Let you take anything A, rectangular A, B, C, D. Let you take this is the layout. We will create generate imaginary light that imaginary shadow that it will fall on the A, and that the shadow will fall on these blocks like this, 2B and 2D and 2G, and 2G it is diagonal, and 2B also it is straightforward. And when the light falls on the B, we can easily visualize from the two blocks that this is the A block and this is B block, and that the shadow is coming from A to B, and this A can see the B at what distance it is there. So from that we can know that how much far it is coming, how much far it is going, and how much far it is going, so that we know the constraint. We know that how much space it is having between the A and B. And see here from A to E, this part we know that from what space these two are there, so we can easily reduce when we want to reduce, or we can keep minimum space. If we want to check the C, you have to remove this B and check how much distance this shadow is propagating to C, and how much it is there, the gap between A and C. From A and G also it is diagonal, so here also we can have the shadow, and we can know that how much distance it is from A to G, and therefore we can reduce the space. We can move G to the up to what constraint it, and that is 3 lambda or 2 lambda. We can move up to that. So this we can represent by this. We can take A, B, and D, G, E, and D is in diagonal. G is in diagonal. B is also somewhat diagonal, but not much. And from this we can note the distance between them, and we can know whenever we can reduce the size or something. And this can be processed to up to the chip, and there will be some end in the chip, so up to there we can proceed this shadow based method. And this is a very well method, and This is one of the method, and there are some algorithms based on constraint graph based compaction. Long some algorithms are there, long path method, and some methods are there. Those methods are explained by Tushar and Sethupathi, and this is all about my introduction. I have introduced what is the layout compaction, how it has the problem formulation, and what are the types of compaction algorithms, and what is the weight B and G in the in this graph, and how connectivity constraints and suppression constraints are there, and one of the method I have explained you. And this, and from this I am concluding that some constraints we have to need for reducing the size of the layout. So the from that they developed some algorithms, and we can reduce the area. Thank you.
Hello guys, I am Sethupathi. I am from VIT Chennai campus. I am a master student here studying MTech in VLSI design. So we have been given the assignment of recording a video lecture, and the topic of this video lecture is longest path algorithm. The topic constraint graph based compaction methods for the course CAD for VLSI systems. Okay. So there are basically two conditions for implementing the longest path algorithms. First condition is that the graph must be a DAG, which is direct acyclic graph. The graph should not contain any cycles, and also node should be repeated more than once. So these two are the basic conditions wherein we can apply the longest path algorithm. Longest path algorithms is unlike the shortest path algorithms, it's used in those graphs wherein the dependencies of the next node is dependent on the previous node. For an example, in this graph, the node 8, the value of the node 8 is dependent on 7, 4, 5, and 2. So in order to find the longest path path, we need to know the value of 7, and in order to know the value of 7, we need to know the weights of 6, and so forth. So the algorithm goes as follows. The problem begins in this fashion. If the integrity of any vertex is 0, it is known that we should start the algorithm application from that node, or else it can be also told as the longest path to that vertex is 0. Then if the integrity of any vertex is greater than 0, the longest path of that vertex is the longest path of the previous vertex plus 1. So this is how we calculate the longest path of each node. As I informed earlier, here a concept called as topological ordering is followed. It says that it's a type of ordering the nodes wherein the previous node comes first and the succeeding node is dependent on the preceding node. For an example, if here in this example v is equal to j comma k, here j is left to that of k, which means j is the first node and k comes after that, and k is dependent on j. Similarly, for all the nodes, this particular order is followed. Also, this algorithm has various applications, such as the number of courses required. One such application is that we can calculate the number of courses required to complete the degree. Another application is that we can use this algorithm for compaction in layout designs. Compaction is nothing but reducing the area as much as possible in the backend design, like the layout designs. Here we compute the longest path as we compute the topological order. So this is the graph for reference. So here the red colored materials are called are the indegrees of the nodes, and the green marked materials are the longest path. So initially we start the algorithm by taking all the nodes have the longest path at 0. As the algorithm proceeds, we keep on deleting each and every node until we reach the 8th node. Once we reach the 8th node, we can find the longest path, and that will be shown in the table given below. So here we start the algorithm by assuming that the longest path of all the nodes are 0, and the indegrees is given by the number of edges pointing towards a node is known as the indegree. The number of nodes, so the number of edges moving away from a node is called the out degree. So here we are concerned about the indegree and the longest path. As I told earlier, we start the algorithm by taking all the nodes longest path as 0. So we begin the algorithm from the first node. We can also begin the algorithm from the second node. The condition for starting the algorithm is that the indegree of the nodes must be 0. So we can either start from the first node or the second node. Here we are starting from the first node. So in the first iteration, we are removing this node and we are updating the longest path values of all other nodes. For an example, if I remove the first node, the nodes that are getting affected after this are 2, 1 and 5. So as I explained earlier, the longest path of the succeeding node is the longest path of the previous node plus 1. So here the first node was removed and its longest path is 0. So the third node was connected to the first node, so the longest path has been updated to 1, which is 0 plus 1. So similarly for the fourth node and the fifth node, the corresponding values of the longest paths for the fourth and fifth node are 1 and 1 respectively. In the second iteration, we are removing the node number 4 because it is directly connected it was directly connected to the node number 1. There might be a question why we are not removing the node number 2 even though the longest path is 0. It is because it is directly connected to the node number 8. Hence, if I remove this, it is directly affecting this. We might end up in getting a wrong longest path. Hence, we are not removing the node number 2. In the table given below, we write the following. In the first row, we write the name of the node, and in the second row, we write the previous longest path. So here, the node 1 has been removed, and it was having a longest path of 0. Hence, it is written. So similarly, in the next iteration, we remove node number 4, and here if you observe, the node number 4 had longest path 1. So that is written here. Similarly, in the next iteration, we are removing node number 2, and we are writing the corresponding values of longest paths of node number 2 here. As we remove the node number 2, we can observe a change in the node number 3, because the indegree of node number 3 in the previous iteration was 1. The indegree of the node number 3 in the present iteration is 0, since the node number 2 is removed. Similarly, we do for node number 5 in the next iteration. We see that the node number 5 has indegree as 0 and the longest path as 1. Hence, in the next iteration, we write that down here. Next, we are removing node number 3, and we see that it affects the node number 6 directly. Earlier, the indegree of the node number 6 was 1. Now the integrity of node number 6 is 0. We observe that there is no change in the longest path, since the longest path of 3 is 1. If we remove node number 3, we should the longest path for node number 6 is 2, but 2 is already been assigned, hence there is no change in 2. In the next iteration, we remove the node number 6 and we observe that the longest path of node number 7 will vary. From 7 has become from 0 to 3, it shows 2 plus 1. So 7, the longest path of 7 is 3 now. Similarly, in the next iteration, we will be removing the node number 7, and we find that we get the longest path of 8 as 4. It is nothing but we 3 plus 1. So here we get the longest path of node number 8 is 4, and in the final we get as the longest path of node number 8 as 4, which is the correct result. We can do it mathematically by calculating all the longest path manually. So 1 to 3, 3 to 6, 6 to 7, and 7 to 8, this is the longest path for the graph. So by applying the longest path algorithm, we are able to write the code and we are able to arrive at the result. So in this same fashion, we can apply the same technique to VLSI systems design and for computer design for VLSI systems, wherein in the backend design, that is the layout design, we can reduce the area as much as possible by compaction, and this method is called constraint graph based compaction. Thank you for listening carefully to this lecture. This is Sethupathi signing.
Hello friends, I am Tushar Varapatre. I am from a VLSI Science department, and today we are going to make a video on constraint graph based compaction method, and I have selected the topic of Bellman fold algorithm. What is the Bellman fold algorithm used to find the minimum distance between two nodes? uh, the the use of Bellman fold algorithm, or the advantage of Bellman fold algorithm over the others algorithm, that it's work on the negative algorithms also, and it's also find the negative weight cycle in the graph. In negative weight cycle, we cannot find the shortest distance because it carry on with the loop. The idea is of the algorithm is to go all the edges of the graph one by one by the random order, and to follow this algorithm, that is the uh, that is the relax of edge uv. If a distance of v is greater than a distance of u, then we need to update our nodal value. We can easily understand this algorithm by the this example, in which we have considered 6 nodes, that is S, A, C, B, D, T, um, in which the first S is a starting and T is ending. Now we can consider we can consider this problem between the any two nodes, in which initial value, that is the starting value of the S, we are considered as 0, and all the nodes we are considered as the infinity, as shown in the table. uh, that it is the distance that we haven't know the distance from S to A. That's why we have put all the others node value as an infinity, and initial we considered the starting value as a 0. As in our algorithm, the first position of S we considered as 0, and the others we need to calculate by our algorithm. The first iteration, the value of A is infinite and S is 0. So by our algorithm, that infinite is greater than 0 plus 5. So we need to update the value of our first iteration of A is 5. So as that S is connected to C also, so the value of C is infinite and S is 0, and the weight of the edge is -2. So by our algorithm, infinite is greater than s, the value of edge, the distance of edge is s, and the weight of edge is -2. So we need to update the value of c as a -2. As A is directly connected to B, so the initial value of B is infinite, and infinite is greater than the distance of A plus the weight of edge 1, that is 5 plus 1 6. So we need to update the value of B as a 6. As B is connected to C, D, and T, the C is having the value of -2, and the B, the edge B is having the value of 6, 6, and the 6 plus 2 is 8, and it is -2, it is, that is -2 is not greater than 8, so we can stick with our answer, that is first iteration answer is -2. So the value, so B is connected to D, so the initial value of D is infinite, and the value, the B is 6 plus 7 is 13, so we can update the value of D as 13. And T, in the T node, that the value of 6, the T node is having the value of infinite, so 6 plus 9, 6 plus 3, that is 9, so infinite is greater than 9, so we can update the value as 9. As the C is connected to A and D, so the C is having value of -2, and A is having value of 5, so note the edge weight is 2, so -2 plus 2, that is 0, so the net, that is and node A, the value is 5, so 5 is greater than 0, so we can update the value of A as 0. As in the case of D, the value of C is -2, and the initial value of D is 13, so the weight of the edge is 3, so -2 plus 3 is 1, so it is obvious greater than it is obvious less than 13, so we can update the value of D as 1. So as in our second iteration, we will go with this process again, and as per our algorithm, that is node A, the value of node A is 0, and the value of S is of 0 at initial, and the edge value is 5, so 0 is not greater than 5, so we can stick with our previous value. So in by the C, that is C is having value of -2, and S is having value of 0, so -2 is not greater than -2, it is equal, so we can stick with the same value. And A is connected to B, I mean B is having the value of 6, and A is having the value of 0, so 0 plus 1 is less than the value of B, that is 6, so we can update the value of B as 1. As is the case with D and T, the B is having value of 1, D is having value of 1, so 1 plus 7, that is 8, so it is 1, the value of D is 1 is not greater than 8, so we can stick with our previous value, that is 1. That is B is connected to T, T's value is 9, B's value is 1, so 1 plus 4, 1 plus 3 is 4, so the value of T is 9, so 9 is greater than 4, so we can update the value of T as 4. As in our third iteration, we can carry out this loop again. So in the third iteration, the value of the our nodes cannot be updated more, as we can check it that s is having value of 0, a is having value of 0, so we cannot go anymore on it. So the same value will repeat in this iteration. So we can carry it out this iteration for by that is node minus 1 times, but our in our third iteration itself we are getting the same value, so we are not continuing with this value, and this is our final shortest. uh, Hence, by this algorithm, we can find out the shortest path between the two nodes, and this can be useful in our graph theory. The preceding value of the node that we need to update while the last iteration is carrying out. For A, it is A, and for B, it is we are carried out as A, and for C the last iteration for is S, and for D it is C, and for T it is B. So by this procedure we will find it out the shortest path between the nodes and the preceding uh, node value that we can use for our further calculation in a graph theory, and we can use in a compaction of the layout design, and area we will reduce further by this algorithm.